Hi, everyone. Thank you so much for coming. I'm Leah. I'm the president of IIC, and welcome to our Phoenix BDR.
Sorry, are you unmuted on the call? I should
I
probably.
don't know.
We are awesome.
Okay, we are. Okay, perfect. Okay, so this is basically the breakdown of what we're going to be doing today. I'm just going to give you like a few seconds to like go over it, and then we can start. Okay, cool. So yeah, this is our team overview. As you can see, we have two teams. We have a team for Phoenix and TinyComp members. For Phoenix, we have 16 total members working on it. It's divided into electrical, mechanical, software, and CAN. 16 is a great number. It's definitely much higher than last year, so there's a huge improvement there. And for TinyCart as well, we can see that we have 21 total members, and that's also very good compared to last year's numbers. There's just like some interesting, demographic about basically the members. This is how like our leadership is kind of divided. We have me, Andy, treasurer. We have two basically chief engineers for Project Phoenix, basically. Then we have a mechanical lead for general software, and we have our TinyCart chief engineer, which is Sal, which you will all see them very, very soon. Oops, I messed up. Okay, there we go.
Should be good.
This is some retrospective. So basically last year we had some kind of like major setbacks, which kind of basically didn't allow us to finish, our Project Phoenix. So we thought it's probably best that we change Phoenix into like a 2-year kind of thing. Pretty much some causes of that were like the scope. We had some machine learning issues, and then we had a loss of mech and elect manpower. So we didn't really have enough people working on Phoenix to be able to get it done in the amount of time that we wanted to get it done in. So in order to fix that, we decided we're going to take some more traditional software approaches. Just because with like machine learning, it's like, it's kind of not so developed, and we just had some, major issues running through it. So traditional is definitely the way to go. We're going to also be slimming down on CAN, and we're actually going to buy a steering motor instead of spending months trying to basically create our own. And we're going to bring in more advisors, high bay support for electrical and stuff like that.
I think you moved off the slide.
I think so too. Sorry.
Maybe.
I don't know what's happening. Help.
Maybe the mouse could be where the screen is.
The
move
mouse
the
is
mouse.
other
It's away.
window. To the
Oh, this?
No, like.
Oh gosh.
If you
Help.
They're two different screens.
Andy,
This is
please.
why I'm the slide.
this is Andy. There you go. Okay, so this is the competition overview. Pretty sure I can click this now. Yes. Okay. So what is Project Phoenix? So basically, Phoenix is going to be a completely electrical, fully autonomous go-kart, and it's going to be basically participating in the autonomous karting series at Purdue University. So AKS is an autonomous, time trial spec race. It started in 2019, and it also includes participants like UPenn, UC Berkeley, and U Hawaii. So pretty big universities are participating in it. So we're super happy to be part of them. And yeah, so it's currently a time trial competition with an obstacle avoidance challenge. This is some more of it. If you want to scan this real quick, you can learn more about it. Some competition information. Basically, because it's time trial format, that means only one go-kart is going to be on the track at once, and the go-kart with the fastest lap time basically gets the highest scores and wins the competition. These are some very cool photos, as you can see. This is some of the go-karts from the previous competitions. This is kind of like a cool image of the track. It's pretty neat. This is just the general schedule. So we would love to get the platform completely built and everything by it says February 31st, which is it doesn't really exist, but It's okay. Just ignore that. It's fine. Also, I did it again. Sorry. Ooh, I learned. Okay, yeah. So, yeah, we just want to finish it by February 29, not 31st, because that day doesn't exist. And hopefully we're going to start, testing by then, because that's when the weather, gets nice and we can go outdoors and we won't have to deal with snow and whatnot. And we ideally want to have like at least a month or two of, testing, just so that we can troubleshoot and everything like that. So that's why we want to have it done pretty much by the end of February. Okay, now I'm just going to pass it on to Andy. Woo.
I don't think people are yelling in the chat, which means I think it's working. So this is a little bit of a difference from, I think, some of our past PDRs. I want to quickly go over what our overall approach is to this competition, since it's a little different, and since we're redesigning from last year, we have a chance to kind of take a step back and kind of reformulate just our overall approach, and this will obviously change how we develop the entire rest of the platform. Oh, right, I have a mouse. Hey. So here's like a very brief summary of that. Essentially, as we mentioned before, there are objects lining the track. In the past, this was cones. Currently, they're talking about moving to like those markers you see when roads are under construction, those little retroreflective chips, just to make it so they're, it's a little more difficult. Basically, detect those objects, whatever they may be, track those objects over time, then plan a path using those objects as like barriers. Then for, path tracking on that path, we only have 2 points of actuation here, being our steering angle and a set speed. We'll generate those using a path tracker, then pass those into a control loop. That control loop will generate our actual values to send to the CAN bus. That CAN bus, of course, sends it to ECUs for like throttle, brake, etc. And then the cart moves, the camera sees another object, and then, of course, the loop completes. And so, oh, it didn't work again. There we go. And so here's like a much more visual representation of that. We'll, of course, go over this much more, especially in the software section. But I just wanted to kind of lay it out up front because this will, again, impact the sensors we need and thus the hardware and electrical design. The big thing that we've kind of mentioned before, but I want to highlight again, is that this is a much more, especially worked with Ross, this is a much more traditional software approach. Last year we tried doing an end-to-end approach, just using machine learning based off the camera and just having that infer everything. This time, as you can see, we have much more of a perception to planning, to like local planning, to control, to actuation. All right, now mechanical with Jaden.
All right, I'm gonna try to run through this quick. All right, we're cool. All right, so this cart that we get, every team gets the same one. It's stock from Top Cart, so I'm not gonna go too much in depth into it. The powertrain is 48 volt brushed motor, but all of this is stock, so I'm gonna move on, and this is for the sake of time. So for battery storage, it's also stock from the cart. So bent aluminum boxes. This year we added 3D printed covers on them. Adds a little bit of water protection, but also just protection from people putting their hands on open ports and stuff like that. We're also going to be adding lead acid. So last year our plan was to do LiPo batteries to power our mid-level circuit. The competition added rules in terms of connectors and safety requirements in terms of lead acid. So we're moving away from those and back to safety requirements for LiPo batteries. We're moving back towards lead acid because they're easier to work with, and we're not necessarily concerned about weight reduction at this point, so we're okay with the lead acids. So the smaller ones will be packaged the same way as the ones that we were given by Top Cart. So we have two braking systems. This brake actuator is part of our Auton braking system, which means, and we also have an e-stop braking system, which I'll go over in a second. You can see some of the specs here. I'm not going to go a ton into it. One of the notable points is that it is controllable by CAN, which is super convenient for our controls and software guys. So this brake is mounted next to the master cylinder. Essentially, it's able to push in small increments, so we're able to sort of feather the brake when we're driving autonomously. This is an important distinction because our e-stop brake, which I'll show you guys in a second, is only on or off. So it goes to basically full lock or not at all. This allows for us to corner easily without fully braking. Our design from last year was heavy, so I'll show you guys the prototype. this functioned. The problem was it's heavy. It was our first try towards the end of the year. This is what we'll actually be using as our test bench for the software and controls guys, while a lighter aluminum project is being completed. A lot of this kind of mechanical, software, electrical kind of dance is going to happen because I'm one of two plus people working on the mechanical design, which means finishing prototypes, allowing software and electrical to continue, and then allowing me to continue to work on the mechanical design is kind of important to meet our guidelines this year. So this is e-brake. So this is probably the biggest mechanical challenge for the cart. I'll let you guys read these. Essentially, the most important details is that it has to be independent, remote, non-network based, and de-energize the powertrain and apply the brakes. Something that's important about this is it has to apply the brakes, but it can't be powered by the powertrain, because if the powertrain dies, the brake actuator, so essentially it can't be an actuator powered by the powertrain or power circuit that may die because of like an electrical failure. The other point is the brakes must stop the cart within 10 meters at top speed or lock the rear wheels. I'll go over why this is important later. We're trying to decide whether we want to brake within 10 meters or lock the rear wheels. So essentially the brake must fail braking. I make this distinction because fail open or fail closed, it gets a little complicated when we're working with electromagnets, which I'll go over later. And then the rest of the points I'd already covered. So electromagnet. So essentially, this is the design that we used last year. The electromagnet concept we're keeping the same. So it's connected to the e-stop circuit. When the circuit has power, the electromagnet has a magnetic field, which obviously has an attractive force. This attractive force holds, call it a steel plate, to the electromagnet. When the electromagnet gets disconnected, the plate snaps back via, we're going to use springs, some actuation force that's automatic, which enacts the brakes. Currently our electromagnet is 12 volts. It's on our 24 volt circuit, which means we could increase to 24 volts if needed, but that's something that we'll decide on when we do a little bit more power consumption analysis. So this was our past design. It sort of functioned at the end. The problem is once we reverse engineered the braking force to figure out our speed, we can only go up to about 14 miles an hour, which is something, the cart can go probably up to like 30 plus. We're not quite sure how fast the autonomy is going to allow us to go, but it'd be really dope that it's over 14 miles an hour. So we knew we needed a better solution. Essentially, there's a small range of motion and small brake clamping force because of those really cheap, they're like Amazon drum brakes. Good for idea of prototyping, not great for actual use. So current design is to replace those brand brakes with a second top cart brake master cylinder assembly that's just comes stock with the cart. So essentially we'd mirror the braking, the brake, I guess, mounting, and then we just have a second rotor on the second caliper on the same rotor. This is nice because we know if we push the master cylinder to full lock, it will already lock the brakes because it's proven. The problem is it requires a much greater force to move the master cylinder. We did some testing on this once we rebled the brakes, and that's 180 newtons to full lock. The electromagnet gives us around 25 newtons of force, which means we need mechanical advantage to make up the difference. For us, that means a lever arm. That's where that entire assembly on the last slide sat. Now we're going to put an entire kind of plate at the back between the rear axle and the bumper, which I'll show you in the next slide after this. So essentially, for the actuation, we kind of have two options. Using a tension spring versus a compression spring. I'll start with a compression spring because that's what we did last year. So essentially in that assembly that we had before, the compression springs, when released by the electromagnet, would push out on that plate, which would then pull the brakes shut and then allow the cart to brake. This worked, obviously, but it wasn't quite functional enough. There's two issues with this. One, we have to try to modify this to now work with the master cylinder assembly instead. Two, we aren't sure how to release the spring when not in use. A big thing why we didn't use the master cylinder second caliper solution last year is because we were worried about blowing brake lines if it's always pressurized. This year we're like, well, if you just find some way to release that mechanism where it can just sit flat for the days on end that we're not using the cart, it's a problem that we can solve. The tension spring, it was an idea that I had this year. that image explains why it's not a great idea, but essentially the pro of this is that it's easy to kind of reset and release. So if you snap it around kind of a column, it's able to kind of be reset. All right. So here's the test bench that we have now. There's some math on there if you want it, if you're really interested. I'm going to keep going though, but essentially this will go on that back. That's that back plate that'll go in the back of the cart. The test bench is useful because it allows us, that'll eventually be used for software testing. It'll also allow me to test different springs, different configurations for essentially this. So this was part of that assembly from last year. We modified it a little bit. And this I can kind of change and modify to kind of validate ideas, and then the master cylinder can be pressurized on the other end. So essentially we can do all of this on a test bench. It doesn't have to be on the car, and it can kind of synthesize electrical and mechanical production at the same time. One note I have, Top Cart doesn't provide any brake data. I've called them, I've emailed them. They're like, tough rocks. So we basically have to reverse engineer speed based on max output of the motor that can brake. That's basically the only way we can verify how fast it's going, which is kind of a pain. In the future, we could use store-bought caliper, but I'm not going to get in that right now. So steering motor, this is our past design. It functioned, but we're moving away, so we got a different steering motor this year. So this was one of the first big purchase we made this year. It's essentially in between like the EPOS motor we tried to get working last year and then just the regular DC motor, so integrated servo. So it'll work at 24 volts, which is what we spec'd it at. It can go up to 72 volts if we need it to, but obviously 72 volts goes into high voltage territory, which is something we don't really want to deal with right now. So that plus the 5-to-1 gear reducer will get us to the 20 newtons that we needed based on the force measurements we got off the cart. We're still trying to figure out, our next steps is to figure out how to mount it. This is my current idea. We're also playing around with some other ideas, but essentially a similar design from before. It'll just take some kind of precise machining. So there's a coupling that needs to happen between the motor and the gearbox. But that's just prototyping and machining and fabrication work on my end. So we have our 3 sensors. So 1 camera, fixed focus wide angle this year. Last year we had a little bit of an issue with ordering. The SICK LiDAR is back from ohm past, and then an encoder solution, which I'll talk about in a second. So camera mount, we have 2 options. This weekend we'll be doing some vibration testing with the Formula car. Basically clamping our camera to it and seeing how much the vibration really does affect the camera. If vibration is an issue, this is something I can make in Measle. It's essentially just a vibration isolator that's made out of wire, so pretty simple to make and replicate. But if we want to go down that rabbit hole, we have to see how bad the vibration is first, because if it's not a big deal, we're not going to go into it. Again, this is just a LiDAR mount we've been working on, water jet plastic. So we have 2 options for the encoder. This is the one we were considering using last year, small shaft encoder. Pros, we have one, we know how to interface with it. Cons, it's difficult to mount. The way we tried to do it last year, I realized wasn't going to work because it's threaded in to the output of the motor, which means as you spin it, it'll start unthreading itself. There's ways to work around it, it'd be a pain for me to have to do. The second idea that I had was to do a magnetic wheel speed sensor. It's what like the combustion car has. And there's 2 options that we can do for that, either a sensor directed towards the brake rotor. One issue with that is the brake rotor is getting pretty tight right now, or it can be directed towards another rotor on the wheel or whatever. So this is a little bit more common. It's definitely easier for me to mount. We just aren't sure how to interface with it with software, which is a question that maybe you guys could answer. So we have some other existing mounting. I'll go through this quick. The shelf will keep, but the e-brake will go underneath it. Computer cage protects our onboard computer. We just have to add vibration damping to everything, including this. PCB mounting, we have 2 STM boards this year and 2 Teensies, which means there will be a little bit different mounting for each based on their power circuits and power supply and stuff like that. But same, just water resistant, vibration resistant. Here's a little bit of our initial thoughts on CAN mounting, CAN harnessing, with just distances for everything as the CAN team starts to develop. And our schedule, basically everything we said before, February 31st, guys, remember that. basically end of February. We want to give ourselves a buffer, whether it's a month to finish electrical design or hardware design or to integrate. We just end of February is what we really want to be at. And electrical.
My name is Ali. I was the Phoenix Electrical lead, and I'm here today to talk about our power circuits. So we have our power circuit split up into two different voltage setups. The first being 48 volts, the second being 24 volts. We have two different 24 volt circuits, and then we step down to these 5 volt power circuits. They're not really as important. They're really just going to power themselves. We didn't really have to do much calculation, as they are just powering boards and things like that. So this is a distribution of how we're going to lay everything out. Over here, you see this is going to be our first part of the 24 volts, where we have the brake, the LiDAR, the steering motor, as well as the magnet. Over here, you see how we're going to power the CAN stuff. Over here, we have the STM, and over here we have the TNC boards. Both are powered by the two 5-volt lithium-ion batteries. Over here, we have the other part of the 24-volt circuit, which is going to be transformed into the 120-volt AC. So we're going to start with DC, transform to AC to power the computer, which powers the microcontroller and the camera. And down here, we have the 48-volt, which is the heaviest one. It's going to power the motor controller as well as the motor. Okay, so this is the more in-depth look at the 48 high voltage circuit. We're going to build it with the lead acid batteries of 4 12-volt ones. We're going to fuse it with 315 amp fuse. Usually 300 is safe. We want to do 315 just in case, just to make sure. And it's going to be powered by a relay. It's going to give power to the relay, which is going to connect to the e-stop. So the e-stop is going to watch for everything past it. And what is past it? The solenoid, which is connected to the motor. And it's pretty basic. It's just power, fuse, relay, motor. Not too bad. Now for the mid-voltage system, we have, as I said before, two different ones. The first being just the 24 volts. We have a 15 amp fuse. He's going to be transformed into alternating current, which is going to power the Dell computer, as we said before. We're going to be using 15 amp fuse, and here are the calculations for the total of the 24. So we're combining both parts, and I'll let you take a look at that. And this is what the other part of the circuit, the other part of the 24 volt circuit. We're mainly going to be looking up here as well as the e-stop, and I'm going to go more in depth with it as the slides move on. So this is going to be the top part of the second 24 volts, second 24 volt circuit. We're going to be using, obviously, 24 volt power source. He's going to be fused with 30 amps because that's what we calculated everything was going to take up. And he's going to be connected to a low voltage disconnect, which is going to prevent the battery from discharging based on the value that we set it to. And that is just the top of it. So after the low voltage disconnect, we're going to have two components. The first being the LiDAR, the second being the brake actuator. We put these here prior to the e-stop because we didn't want these to turn off after we activated the e-stop, because we still want to be able to brake and we also want to be able to scan what's around us, and both are properly fused. Now everything here is everything else here is going to be after the relay we set up earlier, which is going to be controlled by the e-stop, that being the steering motor as well as the magnet. So pressing the e-stop is going to both stop us from steering as well as stop us for it's going to stop power to the magnet, which is going to activate the brakes. Both are properly fused again to what we calculated. Oh, and our plan for the magnet is, we're debating again, like Jaden said, we might do 12 volts, we might do 24 volts. We have the buck in case we want to step the voltage down to 12, but as we have the 24 just in case. As for the e-stop system, as I said before, we're going to have both coils connect to an e-stop, which is physical, as well as this e-stop, which is going to be wireless. Both do the same thing. They're going to power down both coils, which is going to power down everything after both relays. And that's going to stop the 24 as well as 48. And this was the best way we could come up with, stopping power to both circuits. As for the electrical schedule, we want to have, as Jaden said before, everything done near the end of February, because we want to have a month in between the competitions just to sort of work out any of the smaller issues and make sure everything is being well. But the electrical stuff, in theory, end of January, and then by the end of February, everything should be perfect.
Hello guys, so my name is Shri. I'm going to go over to the CAN information. So CAN, which stands for the Controller Area Network, and why we use a CAN. So CAN is widely used in automobile industry. It is easy to implement, it is easy to deploy in a system, and it is proven standard for the automotive industry. So we're going to use CAN for the ECUs and all the actuators and sensors. So this is a CAN overview. So as you can see here, we're going to use a single bus which is connected to the separate ECUs for separate actuators and also the sensors. And this single CAN bus is connected to the PC to CAN interface board, which is connected to the ROS, which is running on a PC with UART. So as you can see here, the brake ECU is connected to the CAN bus, and brake ECU control the CAN the brake actuator, which take a CAN signal as the input to control the brake. Similarly, the steering ECU get the signal from the CAN, which controls the servo motor using PWM signals. So this is just a CAN overview. So how are we going to make the ECUs for the brakes and also the for the ECUs? So we're going to use a 10C 4.1 board and also the STM. So 10C is going to use for the throttle and the auto-on brake, and the STM is going to use for like steering and LiDAR. So these boards going to work on like 5 volt low voltage circuit. These boards couple up with the ECU board design. We get the common interface for the power and the CAN. So this is a design of a PCB board for the ECUs. Moving forward to how to power them up. So previously our plan was to use the micro USB hub, but we changed the plan, and current plan is to use a respective power circuit to protect them from the long-term use. So how we can do it? So as Ali explained earlier, like we're going to use a 5-volt lithium-ion battery pack to power both the boards. So there are one power circuit, one battery pack for each set of each type of board. And this is a comparison between the past design and new design. So as you can see, the new design is much more cleaner, much more simpler compared to the last one. This is a 2022-2023 design, and this is 2023-2024 design. So I'm not going to go in much in details, but which is the new design is not yet implemented, but we're going to do that. So overall, summarizing the CAN network, we're going to use CAN 2.0, which is used to network the embedded systems, and messages are already defined. So a single bus is used, as I explained earlier, as a perception data is minimal. The ECUs are split, which has helped us to make a wire routing easier. As Jaden showed you the picture how the wire routing will look like. So if we split the ECUs, it's going to be easier. Also, the scope of CAN bus is CAN bus should not make any decision based on planning decisions. So this is done to avoid needing sync ROS to the bus state. Also, the bus should not be bus should connecting the actuators and sensors. So this is a quick overview on a CAN that we are planning to do this year.
All right, it's still alive. That's good. All right, so here's the software platform information. I think I was introduced, but I'll do it again. I am Andrew. I am the software lead and also one of the co-chief engineers this year. As we go throughout this section, I want to highlight some of the new members who have been working on these software components. So if you think you need any more like in-depth detail than maybe said, feel free to ask and we can clarify for sure. So, cool. So in ISC tradition, we're still using ROS 2. In this case, it's going to be on that Dell PC that's been mentioned throughout the talk. So this Dell PC, we don't have the specs up here, but it's very powerful. It's actually significantly more powerful than the old NUC we had. The main deal, or the main reason we do this, is to have a GPU for image processing, which will allow us to offload work and just make that a lot more efficient. And in terms of ROS versions, we're using ROS 2 Humble. Thankfully, we have a stable version of ROS that is like usable, or at least in ROS 2, that was we kept having to use like Galactic or versions that kept going out of date in the next year. Finally, we have an LTS that's like stable. So I want to quickly address why we're doing a redesign, because last year we did a lot of work into an end-to-end design and had a lot of that infrastructure built up. So I'd say there's like 4 main reasons. First, what we ran into was we were planning to automate a lot of the data collection. The issue with that is that because we're using cameras, I don't know why this didn't occur to me, but because we're using cameras, that means that whatever environment you're using to automate that data collection, which in our case is our simulation, needs to be photorealistic, because that's the data it will be inferring based on. And so we found actually making that work is very challenging, especially because there's very high compute requirements. So especially in things like sims that are more tuned to this, like Carla, require multiple GPUs because one runs the sim and one does inference, which is definitely outside of our capabilities. And then as well, since I'm actually going to be graduating this year and have been the last person to have worked on the software half of like Ohm and Yeti, I want to just pass down some more fundamental knowledge, just like, theory of planning, of, tracking, that sort of deal, just to make sure that keeps on through the club. And one of the other major benefits is that unlike end-to-end learning, this is going to be much easier to test individual like modules, rather than just having to get all of it trained, and then we can do it all in one chunk. And by the time that's occurred, that's the end of the year, and that's what we ran into last year, where you don't really have time to be a bit more agile with it. There you go. So here's the ROS node graph. I'm not going to, there's not much you can get from this at this distance. But the big thing I want to show with this is that we essentially have a straight path from our camera, the OAK-D, if I refer to OAK-D, it's our camera, through our autonomy stack, through the good old drive mode switch where we can select Teleop or Auton, down into Phoenix IO ROS, which we'll touch on later, where we have our control algorithms. That connects directly to the CAN bus over UART, and then that, of course, actuates. And so of this, we actually have most of this set up from last year, which is really nice. So really, we're just focusing on kind of this path here, which is the autonomy stack. So first off, I want to have Jared present the object detection.
All right, I'm Jared Wensley. I'm working with the perception. So with object detection, we want to determine the track boundaries. The competition hasn't decided on what we're using, but most likely it will be orange cones again. To do this, we're going to be using OpenCV instead of a neural network like they attempted last year. These detections will be published as poses, and this will benefit us if they decide to not use orange cones, and then we can change our front end and our back end independently. The front end will take an image and then find the center point of the cone. And then the back end will take that center point and then project it to the real world. For the front end, we're given an RGB image. We convert that image to a hue, saturation, and value. Then we mask those orange pixels. We create contours around the masked object, and then we find the center point. Now we need to distinguish between a cone and other masked pixels. My current implementation is using the dimensions of a cone, and that can be shown here by the NASA rocket right here is not returning the center point, which is displayed with these blue dots. It is not perfect, and I haven't perfected it. If anyone has suggestions or different ways of distinguishing, I would love to hear that. Thank you.
And real quick for the back end, since this is a lot more advanced, but we've done this before on Ohm. So for the front end returns the center pixel values. But as you mentioned before, we can then swap out the front end independently, which is nice. And then all the back end is doing is simply taking those center pixel pairs, projecting that to the real world. Thankfully, we have a depth camera, so this is much easier. So basically, my current process, which is actually just slightly modified from good old white line detection from a few years ago, is to basically get the transform from pixel space to camera space for that pixel, just using the camera intrinsic matrices. Find the depth then at the same pixel in the depth image. Then you can just treat that rotation as a ray and that depth value as a magnitude. Just solve that for the components of that vector, and then that's your point. And then of course you have to transform that to the point of view of the robot. But this should be fairly simple. Again, we've got most of this done in the past, but working with the depth images is something we're going to have to mess with, especially in terms of really testing those sensors a lot more on a vehicle, seeing how things like vibration potentially impact it, because it's not using lasers or like structured light, it's using just the stereo pair to create that depth image, and we just don't have a lot of experience working with that right now, so hopefully things like, as Jaden mentioned, testing on the combustion car should give us some early data here that we can use to see if this is as viable as we think it is. Oop, skip a slide. All right, so then given the poses, this slide and the next one kind of are really just building into planning. Given those poses from the detector, we'll then track those over time. This is less, at the moment at least, in our planning, to track if the cone goes off screen, and more just to assign identity to the cone. So basically, we have a detection here, we have a detection here. Is this the same cone over time? That's useful down in planning, as we're able to do things like see if there's a new cone on screen or whatnot, and do things a little more lazily. So my current idea for this, just searching around for what the normal computer vision approach for this is, was to just have a Kalman filter for the state of each cone on screen. When we see a new cone, initialize it, have velocity and pose as the state variables, take a pose in, and then track it over time. If the detections we see are close to the predicted values of the Kalman filters, within some threshold, we then say that's the ground truth for the Kalman filter, update the Kalman filter, and then, of course, we can maintain that identity for that track. I'm fairly certain this will work, but again, if anyone has more experience in this, I'd also love to hear it, because I'm new to object tracking. One of the cool parts of this, and again, this is something we'll just have to test and see, is I think because we have velocity in those Kalman filters already, I think we can treat this as almost like an extrinsic measurement of our speed, because of course the cones move opposite to the way we do. We're already tracking their velocity. So I think what we can do is essentially just average these Kalman filter states and use that as essentially a very, very basic visual odometry. This basically comes for free, but I think it would be a fun little experiment. So we can try that out and see if it actually improves our accuracy there. All right, so this is probably where there's going to be the most complexity of any of these sections, and that's our planning algorithm. So of course, we have our tracks of the cones over time. How do we actually go through them? So at the moment, the general gist of this algorithm, or the general idea, is to just pair those cones across the track, find at the moment just center points, and then drive through them. There's been discussions of a lot of ways you can make this a lot more advanced, like biasing to one side or the other to have like sort of racing lines. But I want to start with this just to get the theory down. And then this plan would just, of course, be replanned whenever a new track is created on that path. I'll get to the ODOM thing in a second. So there are actually a lot more edge cases to this than you would think. It looks really simple on the slide. In that case, maybe it is. The biggest thing I'm concerned about, because we ran into this back in the ohm days with the white lines, is that even with this wide-angle camera, think of the benefit of sim, I can see this now because I have the camera set up there. Because sim is set to the real life, we also will have this issue here too, or same scale. You can see when you enter a curve, you can see everything fine. Halfway through a curve, you lose sight of the right or left side of the turn. So if we don't do any sort of countermeasures, you can see how this, like these two here, could be right and left sides of the lane. So we're going to have to deal with that case and not plan right off the track, which is of course the exact opposite thing we want to do. So my current idea to mitigate this is to have some way of detecting if we have both sides of the track detected and simply reject stuff in corners. This works because if you looked at those images, we do see the whole curve here. So we will have an accurate plan here, I believe so at least. Again, have to test it and make sure cones aren't obscured. But you can think of like having points throughout this whole curve. If we just reject it while in the curve, then we can continue following the path we already planned. Once we leave the curve, we can start planning again and correct for any errors that we came across. How to actually determine that is kind of an open question. It's one of those things that you brainstorm an idea, I throw it on the whiteboard, and then it's actually fairly challenging. It's almost like a classical machine learning problem of like classifying right and left. Once you get into like S-bends and stuff, it gets a little funky, so we're still working on that. I think that's going to be where a lot of our like actual algorithm design is this year. The other thing I'm curious about, and just if anyone knows this later, come talk to me. I'm not sure how persistence of path normally works in this sort of like ROS area. In the past, of course, we used a lot of like nav2, navstack for ROS1. So I'm not sure if you can consistently add new points to this path, or if you keep republishing the path. I'm just not sure which one tends to work better or is more conventional. All right, so I mentioned this in the path, but this is one of the neat things about using this strategy, is that it's all very local to the cart because, of course, we can only see close to us. It's also replanned very frequently because we're moving quite quick and there's a lot of cones. Because of this, the only error we care about in ODOM is actually from two cases. One, it's from where we are now to us, the time where we reach the last point in that path, which only occurs in corners when we lose both sides and we just have to plan on the path we created. Or in the case of when we plan to the next time we replan, and then it effectively corrects any error in ODOM that occurred. So I think we can actually use this to considerably minimize the complexity by simply not using SLAM. Because these cones are, they're kind of a map if you want to think about it like a local map, but because they're updated so frequently, we don't actually have to do any sort of like maintaining a map over time, and thus long-term error really doesn't matter. It's only short-term error. So my idea is to just use a Kalman filter with a lot of preferably good ODOM, and then just minimize that error in the short term, and then in the long term we just simply don't care because there's nothing to maintain long term. It's only relative to that short span of time. So this is another thing that we really have to test because this could fail pretty badly if there's not much you can do to counteract this if your ODOM just isn't quality. If that happens, like come the spring when we start testing, it should be pretty easy just to throw like RTAB map or a VSLAM in this, not to map but purely just for localization and ODOM correction. But at the moment, we're thinking of using the encoder, the IMU, and the camera, the tracking that I mentioned earlier, my little experiment. And then in Sim, I've been trying to get just the visual odometry part of RTAB map working. You can actually only use that part of it instead of doing full like loop closure and all that. Sim isn't quite detailed enough to test this, which is annoying, so we'll have to test this in real life. But hopefully that should give us another more stable source like we did on Ohm with like the T265 RealSense. All right, so now to Nick with path tracking.
Hi, I'm Nick, as Andy said, and I'm going to be going over the path tracking concepts for this year. So with path tracking, we have our node, hybrid pure pursuit. I'll get into why it's called hybrid at the moment, but this is just basic pure pursuit, and it will give us two commands for our steering angle and our set speed, which we'll supply to the cart, and we'll be able to calculate our Ackermann angle and our desired velocities. We're also going to be using the LiDAR scans in this pure pursuit, which I'll get into in a minute. But this is just going to be for obstacle avoidance on the track. So this is a little bit of overview of the pure pursuit. So this is just basic pure pursuit. I'm not going to get too much into it. Essentially, we just need to make sure that we tune values that are kinematically feasible, especially for our look ahead distance. So our radius of like point intersection. We want to make sure that we tune a value that is feasible for our Ackermann angle and we can actually obtain. And down here, this is what our equation will be for determining our velocity that we're going to be setting. So static friction, we're going to be just having at 1 right now. And then we have our gravity constant and our turning radius, which is determined by the instantaneous center of rotation. That one. Okay, so this is a little bit of a visual representation of our concept. So this is where our cart would start. We generate a path based off of camera data to a point, and then we follow this path, and we follow this path again. We're going to generate another path, and as you can see, there's an obstacle in the way. So we're going to be like, no. So we're going to have a flag that tells us, okay, we have an obstacle in the way. So now this is when we switch to a stateless state LiDAR control. So our plan is to have LiDAR detect this, and to be determined as an algorithm to navigate around this. But we'll navigate with the LiDAR, and then we'll generate a new path. And then that path, if it doesn't intersect, we're just going to follow it. And that's the overall concept. Right now, we don't know exactly what we're going to be doing with the LiDAR algorithm, but we do have a AEB algorithm that was developed to detect objects in our path. So And then this is a little bit of a demo of what we have currently in Sim. So as you can see here, I give it a point, and the robot will try to move to that point. It starts drifting a little bit because of some funny tuning values that we need to set in. But then you can see on RViz in a second here, I add a visualization marker, and this is going to generate our look-ahead distance as the red radius based around our rear axle, and then the green line is going to be our predicted path, our predicted arc that we're going to be taking. It goes zoomies, it goes far. But to be determined and to do, I guess, is to tune these values. So our min and our max look-aheads, as well as our speed multiplying constants for our look-ahead, and as well as some static friction things and other coefficients. But if anybody also has a standard way of finding these values to at least start and get a better idea of what the value should start as when tuning them, that would be really appreciated, because I have no idea where to start for tuning these values. I think that's me.
Hello, my name is Harry. I'm going to be doing the speed control and the control loop for the Phoenix. So basically we have two loops. One will be for the braking system, where we control the brake, and one will be for the DC motor, where we control the speed of the car. So the input that we'll get from the previous node will be what speed we want the car to be going at. And we'll have the output speed, which will be the speed of the car, and I'll explain how this kind of interfaces together in the next slide. And then for the loop, we'll actually have a can command. So we'll have a value between 0 and 1, which we'll send to the ESC for the brake or the throttle system, and that will be sent to the can. So we want this to be reliable, but also easy to tune, so that on different tracks, we don't have to spend a lot of time tuning this. Even if we lose a little bit of accuracy, it should be fine. So this is a very basic initial look on how the control loop will look. So this is the model in Simulink. So this is the DC motor that I've modeled just based off some parameters from the motor's data sheet. And then we're gonna have a PI controller, so basically it's a P and I component, and we'll set the derivative term to this P0. So again, we have the desired speed here. We have the output, the current speed we have, and based on those, we'll subtract them. We'll have some kind of error value here that we'll send to the PI controller, and then based on the gains that we'll set, we'll then output a command signal, which will go into the DC motor, and then we generate the speed again in the output. We measure that, and then just keep looping. So we haven't actually tuned the parameters yet. For the DC motor, I'm planning to just actually model the parameters in Simulink first as kind of an initial guess, and then fine tune them on the actual cart. But for the braking system, I don't think I'll be modeling that in Simulink, since that's probably going to be much more difficult than a DC motor. So for that one, we'll just be we'll set some initial parameters, and then we'll tune those based on how we see the car behaving. And that's pretty much it.
All right, so you've seen it a few times now, but of course we're still using Gazebo. This is Garden, because Gazebo Classic is not even available, I believe, on the current ROS 2 version. Still always a bit finicky, as Gazebo always seems to be, but we have cones now. It's crazy. Thank you, he's not here, but Tony, for the cone model. It's very good. So you can see we actually already have a bit of our stack running in Sim here, just the cone detection and the cart. This Sim, as you'll see in a second in this video, it's kind of accurate. Like, it's definitely a rear-wheel drive go-kart, but I would not tune a control loop based off values from this. But it's still nice. It gives us a good place to test. I was struggling with the keyboard controls here. Gives us a good place to test like kinematics. And what you can do in Sim, I'm very proud to announce, right? You can do donuts. So it's accurate enough. That's all I care about. click. There we go. All right, so not going to do much with this, but nice thing again about doing a simple approach is that we can simulate literally all of it, minus the control loop, annoyingly. I wish we could, but again, frankly, Gazebo is not going to be accurate enough to make realistic values. You can't like simulate, as far as I'm aware, like a braking system, at least in the newer versions. All right, so last bit from me. I just want to touch on the physical use of the cart, since this is something that has been, especially on Ohm, a bit of a pain. So because we're not using the old System 76, we don't have a laptop we can just slap on the cart. What I've done last year, this is already working, is have the computer run a Docker container with all of our code in it. So essentially we just have a standard Docker container for the club, throw our code in this, set that to auto boot on the Dell PC, and then also with that, I have a script that just sets an 802.11 ad hoc network on the Wi-Fi card on the computer, which is actually really strong. It's like an external antenna. It's kind of crazy. And then with this, just because ROS2 obviously just works over the network with Discovery, you can simply connect a laptop to the Wi-Fi network set up by the cart, and then we can connect to it and do whatever debugging we need. Now, the major benefit of this compared to prior years is that we don't have a home router on the cart anymore. This is obviously nice because unlike the likes of like Yeti, where we can just kind of shove it in the body, having a home router on a go-kart is a little silly, and this is just a much more elegant manner of doing that. So general schedule for us, it's always a little hard to describe these because we do everything in a pseudo-agile manner, kind of week by week. But I really want by the end of this fall semester to have an initial prototype complete. We have so little to do that I think this is very achievable. And then basically from that end of December, so that January to CDR being in mid-February, go back, evaluate it, look at what we need to change, make those design changes, at least in design, before CDR so we can make sure it's all accurate there. After CDR, implement that feedback or anything else we needed to do. Then same as everyone, I don't have February 31st up here, but early spring, make sure everything's ready to run on the cart. We need to use every day we can. And especially, I think more so than the other sub-teams, Suffer is going to have most of its work in the spring, especially on like the control side. There's going to be a ton of tuning here, a ton of last-minute redesign, as there always is. But really, the most we can get done before this time, the better. And especially since Sim is a lot more usable this year, hopefully that should be a lot easier to achieve and really make it, succeed a little more. All right, so before we get to questions, I do want to briefly highlight a project that this isn't even a PDR for. That is TinyCart. If you're here last year, you saw a brief bit of this. If you haven't been here for a while, then this should be new. This is our entry-level program we're running right now. The majority of the club is actually in this and not in Phoenix at the moment. So I wanted to give it some time in the light since it's something we're putting a lot of effort into. I'd like to invite Sal, the program lead.
Hi, I'm Sal, and I'm here to cover what we're all here for, TinyCart. Right. So essentially, it's an introductory project for new students joining the club, right? It's a fairly simple, project outlook. So we divide up team members into teams of 4 based on their engineering disciplines, right? We aim to have at least one software engineer, one electrical engineer, and then one mechanical engineer, and then another engineer in the team. And essentially, they're tasked with crafting this autonomous car that can navigate through a walled circuit. They will be given a little STM32 LiDAR, of course the RC car, and the a 2D LiDAR as your only sensor. This is the overview. And then, so the method that the students are going to be using is a quite simple method. It's called a Ken run, sort of follow the gap sort of thing. So where the LiDAR readings tell you where to go. So you have the LiDAR readings, right? And then you get you follow the gap, the predetermined gap. So what a gap is, it's up to the teams to use, the teams to set. So in our experience, a gap was 10 adjacent points, LiDAR points that were at least 1.5 meters in distance, distant readings from the car itself, from the LiDAR itself. So that's what a gap is. This is a fairly simple algorithm, as we've encountered in the past. If there's any little hole in the track, or just anything that I might see as a gap, like for example, like right angles, it usually tends to go to them because it sees them as a gap. So that's what they're going to be doing. Pretty simple algorithm, pretty simple to implement. And then current state of TinyCart right now, it's running. I've already given 4 classes. Great young students we have in the team, and they're doing great right now. We still need one more class just to finish that off, and then it'll be followed by supervised build days, where me and some other people who have completed the project will be able to help new TinyCart teams. And yeah, it's a happy group right there. That's it for TinyCart, guys.
All right, so that's all for the main PDR presentation. Of course, that is always half of the PDR presentations. So for general questions, critique, I want to first start with kind of general design scope stuff, then move into software, then move into hardware, just to kind of control this a little more than us bouncing back and forth in case we get onto like, you know, a bit of a chain of questions. I'll make sure I'm like looking online as well. But yeah, anyways, I will open, if I can, thank you, mouse. Oh, there's a lot of questions. Okay. Because yeah, if you have questions, especially on the general stuff, feel free to ask them now. We can get into the whole proceedings.
Yeah. So the LiDAR is used purely for detecting the obstacle at the end?
Yeah.
Okay. Because there's no other markers you could use with the LiDAR to help with localization?
So theoretically we could. It's still only a 2D LiDAR though, and the go-kart track being a go-kart track is considerably less feature-rich on a 2D plane than even like IGVC was with the barrels. And so we may even be above the cones. And I don't want to bet on there being cones in case they do change that. So yeah, at the moment it's just for seeing the box. It was way at the beginning of the presentation, there's that 3 Home Depot boxes. That is actually standardized in the rules. It's specifically Home Depot, only Home Depot. We could theoretically use the depth values and basically do depth to point cloud to laser scan. The only reason I didn't plan for that and why I want us to have a LiDAR on board is because I haven't tested that, and I don't want to plan for something that won't work, especially because stereo cameras can have some trouble with flat walls, and those boxes are flat, so, you know, but anyways, yeah, for the moment it's just for that purpose. Yeah.
Could you use it for localization? And it sounds like it'd be very difficult.
It'd be very much a last-minute gamble to get localization working better. I don't want to plan on it just based off the theory. Yeah, if there's no cones, it's like basic gazebo is actually accurate for once in that case. And yeah, especially if you're with actually you were with OPE in the past, how hard it is to get sim working without a bunch of random geometry placed around to give it features. Cool.
Do you have a plan if there's no cones for track running?
What do you say?
I mean, do you have a plan for if there's no cones?
Right. So right now they've. So I'm actually on the rule committee there because they're so inconsistent with this. I'm like, gosh darn, I'll just do it. And so right now it's basically the competition has formats. I didn't get too much into this because honestly it's not really that relevant and they keep changing it, so I kind of don't care. They have 2 forms. They want to have one which is identifier lists and allows pre-mapping, I believe. So that's more just doing like something like machine learning inference like we were doing last year just to stay on the track. The problem is the track isn't very well maintained in terms of like lines, so that's a very, very challenging thing to do actually. The other one is going to have some sort of marker, and that's really what people are aiming for mostly. I've been pushing towards actually little markers instead of cones because I think that would be way cheaper than having like 150 cones. You can have those little cheap things you can get off Amazon. But regardless, we'll have something marking it. And so because we can just swap out our front end in our design, that should be a pretty minimal change in our design if they do end up changing it. But yeah, I've gotten that much out of them that there will be a marker category with something. And like, okay, that's fine. Whichever it is, we're fine with.
What is the track environment? Is it going to be a solid like piece of concrete, or will it be a track with grass around it?
It's, so you can see it early. Oh. Can I? There we go. Way back. You are a smart man. So. Yeah, that's true. You're smarter than I. So you can see here, this is the actual exact track. Jordan here actually scanned this into sim with correct sizing, which is quite nice. So yeah, it is marked with grass. It's marked with just about grass. And so a lot of the teams were talking, for those that were attempting to infer, they were trying to do, like, use the grass as the edge, but then the lawn crew just like doesn't water for a week, and then it's just dirt or something. And you know, that's approaching like considerably more complexity, unfortunately. But yeah, thankfully the track surface itself is pretty nice. I mean, it's a go-kart track, so it's not like the IGPC parking lot where there's just like a storm drain in the middle of the course and it's like at a 45-degree incline or something. It's flat at least, which, you know, especially because I should have mentioned this, but it should be inferred. Everything we're doing is in 2D for planning. So if we were at like Laguna Seca or something, this plan would not work very well at all. But you know, it's a go-kart track; it should be pretty flat. We also don't have a suspension, which would make that pretty rough. But you know.
When you guys go racing at Laguna, let me know.
I will. Just wait. Any more for general?
Yeah. For your guys' milestones, you have dates
Right.
when they end that are almost in chronological order. Do you have dates when they start?
Just when the previous ends. Yeah, I'm aware it's... So I tried to fit a Gantt chart here, and it didn't work. It was very busy, so I figured this is the easiest way to view it. But yeah, basically when the last... For each team, so like software design complete to software initial prototype, just consider that like between that time, the next one is being worked on. Yeah, I know it's not the easiest thing to read, but I get it. I promise this is better than the Gantt chart.
Okay. Yeah, I would definitely, especially for your hardware teams, manpower's always been an issue. Having realistic start and end times and knowing when you're parallel pathing like 12 different projects versus one is very important. And then also being realistic with like you're going to stop working during midterms and finals. Like,
Yeah.
It's just going to happen. We always plan to work during midterms and finals, and like Christmas we never do.
Yeah.
So being realistic, like during that time, you're working on like maybe half a project. Also anticipate burnout.
Yeah, I mean,
You'll
that's
have
just
massive
always a...
drop-off. So I would watch for software having burnout during the end of the year.
Oh yeah, that's why I was trying to get a prototype. Originally, I had the prototype for software actually marked at Thanksgiving break for that exact reason. But then I'm like, okay, that's like that. We're never gonna hit that. So I wanted to push it back. That's why I have December 1st listed. Preferably before finals, I'd like to get this done so we can kind of step back. The prototype's there, like it won't be half complete. Go do finals, take a break, come back, and then evaluate what we have with a fresh mind. I don't know what Mechanical's plan is in that regard, but.
I mean, the issue is like it's still small. We thought we had more people, and then obviously people start dropping off as the school year starts.
Could you come over here for the mic?
Oh, sorry.
Thanks.
Yeah, totally. So for Mechanical, there's a lot of issues that we had last year with small manpower. Those issues still exist. The cool thing now, though, is that there was work that was done last year, which means test beds that were done last year can still be a thing. The Mechanical thing, it's like a little bit more software related, where it's going to be a little bit more agile week to week. We're going to see what we can and can't get done. That's really convenient because it's basically one person-ish. So it's what we can and can't get done. Basically, I'm going to get done as much as I can in the time that I can, which means it's only going to be planned monthly, weekly. But that's kind of it for Mechanical. For Electrical, you can talk about what your plans are if you want.
It's similar to what Jaden said. If anything, electrical is one of the lesser manpowers of the group. So we want to take as much time as we need to have as many safety precautions as we can. Because I know the year prior they made a lot of not a lot of mistakes. I don't want to say they made a lot of mistakes, but they made from what I understand, they made a few very fatal mistakes, and. Sorry. But I don't want to rush anything, because if we did rush anything, it could be really bad. And as we don't have the most manpower, nor do we have the most experience working in ISC. This is my first time. I want to take all the time we can, and I don't want to overlap over anybody. So I will work alongside Jaden, try to meet her deadlines as possible. Just match up with her.
The big thing with deadlines is less about like forcing yourself to meet them,
Mhm.
but more just being realistic when you've fallen behind.
Exactly.
Because we were pretty poor with that last year, where we missed deadlines and we just kind of extend them because we want to try to do it right. But the big thing is like design fab for like finishing January 31st. Like when it becomes February 1st and it's not done, don't just extend the deadline. That means like you need it like SOS.
Exactly.
Call in some alum, call in like faculty.
Mhm.
But like knowing having realistic deadlines, and then again back to the realistic deadlines. December 31st, February 31st. Those are not real deadlines. I'll be serious. That December 31st deadline should be like a week before finals. February 31st should be a real date. But like be realistic with so when you see them approaching, and like if you're a week out and you're like, bro, like this is
not
far
good.
from done. You know, like be honest with yourself of when you need to be calling in more people, especially you know if you're running a team of 3 in elec and a team of 3 in mechanical.
It's
like your manpower, you guys are gonna like burn out. That's just what
100%. Yeah.
teams. Trying to prevent that though by being again realistic with the deadlines. And,
Exactly.
you know how much progress have you made? Will really help.
Which is what I anticipate. Honestly, I don't. It's not that I don't see us meeting the listed deadlines. It's more so we want to get started, see how long everything is going to take, see where we are in this time, and then we can sort of reevaluate. Oh, do we need somebody to come help us? Do we need to call a a graduate student to come evaluate where we are, what we need to do next? But that's in terms of deadlines. We want to work alongside each other to see when we can finish everything.
I kind of want to expand on the deadline discussion. And it's kind of like based on the milestones. How do you work back from your milestones, and how do you split up units of work? Do you have like, would you have like a weekly or 2 weekly sprints or something like that? Or one thing that I've personally experienced and it's helped me is you take the big picture, you break it into its very small components, and you're like, okay, I'm gonna do this small piece today, I'm gonna do this small piece tomorrow, and go like that and fill the calendar basically.
Yeah, because I guess like kind of what we did last year for Mech, like a big one was getting drive-by-wire done, or like drive-by-wire was what, brake, steering, accelerator, breaking it into like a 6-week goal into 2-week goals. You know, again to try to catch stuff earlier.
Yeah,
I don't know if you have that in your Gantt chart or.
This year for Phoenix hardware, we have meetings every 2 weeks. Basically, so at that meeting, we essentially, what have we gotten done? What are we doing the next 2 weeks? We felt like for hardware, this makes a lot more sense because sometimes things take time. People get busy, like with finals or exams or anything like that, especially it's been midterms. Like, you may not get done you may have nothing done in a week. So for us, the 2-week system has kind of worked a little bit better. Is it all in a Gantt chart? No, but essentially, yeah. What have we gotten done in the 2 weeks? What are we doing in the next 2 weeks? So very sprint-like in that regard.
Yeah. If you're doing every other week meetings, I would be very strict with your milestones.
Okay.
Because writing it off for one meeting puts you 1 month behind, and that's over 10% of the year.
Yep.
Which means like once like you can completely murder your timeline by being lax in one meeting.
And I mean, usually Jaden and I were sort of, taking control of the hardware. We're in contact like almost all the time. If I go in to do something in IC, I will always tell her, hey, this is what I got done today. This is what I expect to get done within the next few days. For example, like diffusing calculations or something. I would tell her, hey, I plan to work on this. I want to take 1 day, 2 days, whatever amount it is. And we want to keep that constant communication because we want to know at all times where we are like with each other, because the hardware we know is very can be very complicated if you don't have that communication.
So, okay, I guess Brian, we'll have Jordan go here. He had his hand up in real life, and then we'll get up to you.
I'm just curious, what's the goal for the prototype? What do you want done for the prototype?
Oh, yeah. I'd like to, honestly, just the complete thing in Sim. It doesn't have to be, working. As long as, the code isn't crashing. It's, my standard. It may not be perfectly tuned in. We may find out, ODOM drift is way worse than we thought. But I want to find those things, essentially. So, yeah, having all of those core tracking, detecting, path following, and path creation to be complete in some form. And then, so a form that basically we can actually do some of that evaluation on. So obviously, it's not going to be perfect, but just enough to, to test it out and see, is the general design even viable,
Cool.
All right, Brian, I will let you speak. Hopefully this audio works. Oh no, the audio is not working. Uh-oh. Let's see if we... All right, try again. Oh, it's not working. Oh, okay. Thankfully, do I have an audio jack? Oh no. Oh, I do. Thank you, Dell. Superior laptop engineering right now. All right. Oh, it's still not working. This is tragic. Okay, just type it out and I'll mess with it. Oh, it was. I see. It was going to the microphone.
Oh yeah, because it's both. There's an audio output. On
Oh,
the microphone.
it's still not working. Oh, this is. Yeah, he's typing in chat. Yeah. I don't want to mess it up by detaching it. Headphones. Built-in
Sorry,
analog.
you might have to just type it out.
AB is hard.
He is. Yeah.
We have the B and not the A.
He said something.
Yeah. What practices for project management in terms of tools and software sharing with hardware for managing the backlog? Yeah, so that's honestly something we're going to have to standardize a little more as we go on. Right now, we essentially have two tracking, one for hardware, one for software. In software, I'm using, I don't know if you know this, but they actually, in GitHub features and GitHub issues and projects, they actually added a Gantt chart. So you can actually use it like, Azure DevOps. It's essentially the same thing now. So that's what we're using on our end. We also have a master, like team-wide, not super detailed chart that me and Jaden share. And then I believe hardware is using like essentially just a manual version.
It's just like a manual Excel sheet essentially. So we have a list of all of our people. Everybody has everyone's name who's on the hardware side of Phoenix is in there, and then the project that they're working on is updated, and then it's essentially just in progress, complete, or haven't started. I mean, that's basically how I've been tracking it so far. Not in a ton of detail, but I'll take a thumbs up.
Hey, he got a thumbs up. Thumbs up's good. All right. Any more general? Yeah.
So, for software, are you guys doing reviews of each other's work? And also, is someone keeping track of like interfaces between the different packages?
Yeah. So right now it's a little awkward because I'm kind of the grand master of software. Because I'm just the way graduation staggered. Me and Jordan were on it last year. Jordan graduated, so it's kind of just me left from like the old guard. What was your first question? And then there was the interfacing. What was the other one?
So, are you guys doing for the individual pieces of software you guys are making? Are you guys doing reviews of each other's work?
Yeah, so what that is, so at the moment, that's why it's a little awkward because there's not many people that can review my work. And frankly, a lot of the stuff is easy enough that it would be a bit overkill. Like I have set up from last year, this is why it's so nice to have 2 years, is I had time to set up things like CI, stuff like linters. And I have all of those just test on PRs and stuff. So at least I'm checking my own work against my own standards. Obviously, it would be better to have external reviews, but honestly, I'm not too concerned with the ease of a lot of things we're doing, but especially me, for the newer members, I really want to do reviews. We're starting to get to that point, but we're not quite there yet in terms of just there's not enough implemented to do a review. But yeah, for PRs, I really want to actually enforce, 1, you must pass CI, please build. 2, your test must complete, and 3, I'm to look over and just general best practices, ROS conventions, stuff like that.
You have tests for all your software units, right?
Optimally, we have them set up. I made a template so that the G-test is set up. If you use it or not is up to you, but unfortunately, a lot of these are image-based, which is a lot harder to work off of. But especially in terms of like peer pursuit, and especially the path planning, it's just points. So it should be a lot easier for us to have unit test cases, at least if not for normal cases, for adversarial. Like for instance, that curve example from before. That'll be easier. But yeah, right now, unfortunately, we're doing all the things that can't really be tested. Yeah. But it's set up if we can finally actually do them. The bandwidth is the key word there. So actually, Azim Hafiz has been helping a ton with the electrical reviews, from what I understand, which is nice. On the software end, Jarek Kwan is an advisor still. He's just very busy, and so I don't want to bother him unless I have a very, like if we have maybe even for something like some of the computer vision stuff. Like if we have a very specific algorithm where you're like, hey, can you review this? But especially basic things like peer pursuit, I just don't want to waste his time. But yeah. Cool. Any more general? Because
I will add, Azim has overlooked a lot of our electrical drawings. Like we took them to him. Okay. Awesome.
Cool. And that is true. Bam mentioned in the chat. I think did you change your nickname? I swear that was Brian earlier. Then we can have software reviews with alumni. I guess if any of you are interested in that, I'd be down. Like I said, there's really no one to check me, so this honestly might make more sense, more around CDR if you want to do like a last minute. Just because I don't want to waste your time with like, this is a class and it's like most of our files are like 100 lines long. But yeah, if any of you are interested, definitely reach out. Again, probably more CDR time. That would make more sense once we have things more finalized. But it would be nice just, for due diligence, if no other reason, because again, there's no one to check me if I mess up. Yeah. I guess with that, I want to move to software stuff. Oh, you're not done. Okay.
Yeah, I was just gonna ask, what kind of external resources have you guys reached out for in like the past couple of months?
In terms of what?
Just, I guess, industry. Have you reached out to anybody that's in the industry instead of just the university?
Yeah. You talked to a few people actually, right? Both Magna and Yazaki, I think.
Magna wants to help. So once we have a better question in terms of electrical, Magna gave us a contact, or will give us a contact that we can reach out to them for help. I talked again to the guys at Yazaki, so Brian and then Jeff, the guy who came in and gave a presentation last year. They're still super open and happy to help. They're very understanding of how far we got last year and is just happy to continue to help. Obviously, Yazaki level harnessing is a lot of steps away, so we don't want to kind of reach back out to them until we feel like we're actually ready for them to be useful. So 2 of those are kind of the electrical side.
Do you think that would be a good idea to schedule like monthly meetings with external advisors to try and like review your progress?
Maybe. The one thing is like I don't want to be like, hey, we need help, and then you have monthly meetings with people and you don't really know what to bring to the meetings because you're not quite there yet. I would say in like maybe a month or 2, or I mean even now, like if you have, I'm talking to Ali here. Sorry, if we have specific questions, I think scheduling meetings for certain questions would help. I think more than just kind of random monthly meetings, at least for us, especially because it kind of depends on where in like the cycle of development you're at. Software time?
Still more. Okay.
Harmon.
Do you have any way of recording what everything is doing, like any sort of central data logging? Because when you have the testing days and something fails.
Yeah, so we have 2 layers of that. Obviously, on the ROS side, we have all the standard ROS utilities. Lower than that, though, last year, as part of our end-to-end learning, something BAM pushed me to do. Well, actually, this is straight up required if you want to do training. I wrote a data logging node. Basically, that's for logging the CAN bus activities. So we do have the functionality. It's still like, I mean, this is not going to replace like your vector utilities or whatever, but it just records image with, so image of, where the cart is, then the throttle value at that time, the brake value at that time, the velocity at that time, and maybe something else. So if nothing else, that could be useful in like controls or embedded level debugging. For ROS, again, we can just use this like standard utilities in ROS to log pretty much everything you would want if you have enough hard drive space. Bam has his hand up again. Am I reaching out to Toyota and IBS for support? Please let me know if you need me to shake any trees to get your support from Miles, Noah, or Billy. Okay, yeah. That's the thing. I would love to. I want to just kind of like what Jaden mentioned. I want to make sure we have something that's interesting enough to do first. Because right now we're kind of in that early phase where like we have general ideas, but especially if we get stuck on problems in like planning or something, I'd love to reach out. Oh, I'm getting a shake. That's bad. I like this advanced communication here. Reach out early. Okay, I should take that as a sign to do that. Okay, well taken. Oh, actually, wait. This is true. Yeah, Andrew, this degree was well earned. Awesome. Let's see if you got it. All right, cool. Are we done finally? There's software questions in the chat, and that's why I'm like, I want to get to them real quick. We're good. Andrew, there's a question in chat for you.
Oh, for me?
Probably. Okay. While he does that, I want to briefly go to Brendan had a ton of questions in the chat, and I wanted to quick go through them for software because I think they're just generally interesting. First is, how does the, I believe that was probably image detection, work for uneven lighting, which is a very good question. We ran into this. Hi, Andrew. We ran into this with Ohm last time I did my white line detection there. That is actually something we are looking at right now. I was looking into, the issue is it's always with color, and I'm not sure how this plays with HSV. I was looking into just doing, at first, gamma correction, just because that's nonlinear, see if that helps enough. Otherwise, though, we will have to look into two other solutions. Like back on Ohm, I did like, basically, it doesn't really work here, but in that case, I used like, redefined what like white was when looking at those white lines based on averages in the image. We can't really do that as much because we have to deal with color, which makes it a little more complicated. But yeah, that's definitely something we'll have to work on because you know, that is a major concern. Even in Sim right now, if you're going against into really harsh shadows, it does have an issue. And going down, the object detection, or the planning. So what I mentioned, I had up here for the little animation. I'm very proud of this animation, except for the random thing that's glitched and always shows up on the screen. Yeah, this guy will not go away. I can't do anything about it. Basically, my idea for this, just because we don't have a map, which makes all of this really hard. This is why you have a map, obviously. But because I just don't want to deal with SLAM for just complexity reasons. My thought was essentially, and I'm not saying this is perfect, but this is just a first thought. Because this is in our path tracker, so this isn't the planner, this is on our quick iterating Pure Pursuit. Essentially, plan the Pure Pursuit arc. As Nick mentioned, I have AEB, automatic emergency braking, from last year set up. We aren't doing that on like a ECU level anymore, but I have the algorithm working in ROS. So we can use that to forward simulate the cart, see if we're going to collide with something with some tolerance. Based off this, we would flip basically from just Pure Pursuit to retry. At the moment, again, I'm not saying it's a good idea, but it's an idea, is to essentially just fling the cart at some angle around the obstacle based on the weighting of the points. So right or left in this case. That angle can be tuned because we only have to work with one obstacle, which is kind of nice. So you can kind of make it a little less general. But then essentially, because this is in the path tracker, in this case, like I have here, the cart's now here, it then replans. We continue doing that check over and over again. So basically, it'll just keep swerving, and then naturally, because it's running at like 20 hertz or something, if we can then finally go to the next obstacle, it can go. It's not perfect. I'm well aware of this because of course, you're a go-kart and you're going fast, so you don't want to just spin out and slam into the obstacle. That's definitely something we'll have to think on more. My idea was to look at what TinyCart's doing. Not the Canyon following, but there's some of their interesting algorithms, like shoot the gap a little bit, but then there's some more advanced ones they were looking at that I'm like, okay, we might be able to apply that here since it's so simple and reactive. But yeah, it's definitely an area this is probably the least developed area of the software plan at the moment, because this, it's definitely not fancy, I'll give you that. You had a question, Jordan.
I guess it's more just a random thought. But if you know you're going through the box, could you potentially just place 2 points to each side of the box, and then depending on whether that point falls outside of the 2 cone lines, because you'll always know where those are. Because I assume the box is going to be the back straight. You're not going to talk.
It's on the straight, yeah. Well, so, I assume too. Actually, I don't know, but yeah.
I hope the box is in the back straight, not just like in the S's on the racing line. But if it's in the back straight and you have the 2 cone lines, you could just place 2 points on either side of the box at a set kinematically feasible distance, and then if one of the points falls outside of your lane, quote unquote, or that path that you have, you would just choose the other one and sort of Pure Pursuit around it.
Interesting.
Instead of just throwing the cart into a sword.
Okay, so you're saying essentially just like placing a waypoint on either side and then just using Pure Pursuit.
Or you could even have like a bunch of waypoints and choose which one is because obviously.
Oh, that's almost like DWB-ish. That's funny.
Because if the box is on closer to one side or the other, it could be. You could have it
That's my main concern too. Is that if it's all the box is on the left side and we fling left, we're just fling ourselves off the track, which is bad.
Yeah, but you would have like I assume like 5 points coming out, and then you would sort of just choose algorithmically which one sort of keeps you the most in the lane, but also has you avoid the box.
Oh yeah, you could do like distance from the cones on the edge as like that cost. Exactly. Okay, yeah, that's a much smarter idea than mine. Yeah, that would work.
This is a I'm only pointing this out because this is actually something that F-110 solved.
Oh, seriously?
Yes.
I love
This is
F-110 though so much. It's so
for,
good.
For vehicle passing.
Oh, interesting. Okay.
Yeah, this is something F-110 solved.
I assume they have a document on that somewhere.
There's videos online.
Okay.
As well as all loads of
No,
documentation.
I'll definitely look into
Yeah,
it though.
they use,
That's
like,
good.
option secrets and everything, though, so,
Nice.
as well as, like, a full map. But,
All right,
yeah,
no,
that
that's
would-
useful though. Yeah,
that'd
thanks.
be a way that you can.
Oh, I lost the mouse again. It's so tragic. Oh, and on the LiDAR, this is actually a good point, especially I think Joe will also remember this. The LiDAR, the reason we had that home router on the bot, actually a lot of you remember, the reason we had the home router on the bot was for the LiDAR, because the LiDAR uses Ethernet. What my plan is right now is to just plug that into the Ethernet port on the computer. I have taken CIS 427 networking, so I have discovered how to change an interface. So I'm fairly certain you can just, because it's just a network between those two devices, we already know the IP of the LiDAR is literally on the LiDAR. So we just have another IP in that subnet. I assume we can just use that to communicate. And then we don't, if we had two LiDARs, this wouldn't work, but we have one and we have one Ethernet port, so, works out without adding that extra material. And I think that was it for the ones that were backlogged. Oh, we're getting live reactions in the chat.
The chat is live reacting. Yeah. Aside from that, though, I'm a big fan of the concept for software.
Thank
I
you,
think
thank
it's
you.
gonna be Really sick.
General advice, try to keep things simple, especially in the areas where there are a lot of unknown variables. Yeah, I definitely agree with Kyle's comment. Kyle put basically keep things simple, especially in the areas where there are a lot of unknown variables, and keep risk down. That's, at least, especially on the software side, that's really what I want to push. I really want to get this thing moving. I'm tired of seeing this cart not moving. I think especially in terms of a lot of our problems like manpower, if we can get the thing moving, and then you can make the hype video, that will help significantly. We don't have a snowplow to do donuts anymore, so we need to get back to the autonomous donuts,
You need to get like the drone following the cart as it runs, like in all the drifting videos.
Oh yeah. So Bam, this is another good question. Bam asked why we couldn't just take basically just hardcode GPS points across it. I think that's what you were getting at there. Yeah, so the competition explicitly bans that because someone did that in the past and they were like, this is really lame, ban. Which I kind of agree with because it's supposed to be a race and like, I think IGVC also bans this. I forget. Do they ban just hard coding GPS points around the whole course?
No.
Or no, it's just really, that was our plan and it failed. No, well the issue with IGVC is that it's so tight that isn't, you'd have to have absurdly good GPS signal.
We had so many GPS waypoints. Do you not remember that, man? That'd be great.
But yeah, it isn't allowed in this competition. And frankly, I'm kind of glad because I think having to do stuff a bit more on the fly and at speed is a little more interesting. Oh, this is very random, but I didn't mention this in the slides. I forgot. One of the benefits of not using SLAM is that we don't have to deal with trying to do SLAM at 25 miles per hour in a go-kart, which, again, from ohm we know, at ohm speed, it was already smearing. So I would shudder to think of what RTAB map would do at that speed. This way, we should hopefully be able to hit the, again, I think it's 11 meters per second was our previous e-brake target for our 10 meters. So that's, the hardware limit. I'd like to get there. That's actually quite fast for a go-kart on especially a fast turning course. But the nice thing is that means that gives us an actual reason to optimize like our camera algorithms and stuff to like stay within that time span. So it's like kind of soft real time, which is just kind of fun. We had a good GPS for IGVC and it still isn't acting enough. Yeah, no, I should mention that as well. We still have, of course, the old ohm GPS. But yeah, you can't, waypoint following with that even is challenging. That's another piece of ODOM we could add too as well because that's still around.
So this might be a bit more general, I guess, but for your software, do you have a minimum viable product? I saw that on the slides earlier, but do you have to find for software and how much do you think you like? How much of that is going to be accomplished in the prototype? I guess. Like how much of that will be done? What will you have to do? How far is that from MVP?
Yeah.
What, March, I believe?
Yeah, so MVP is basically March, yeah, because we want to be able to test it. So I have to be a little hand-wavy with it just because it's kind of hard to define. I guess context I should add, because I don't know if I've stated clearly enough. Pretty much all of like the framework stuff is done. Actually, it is done from last year. So literally all we have to do is what we presented. So I'm gonna try and get a form for that, like that, not MVP for the spring, but done at the end of the semester. And then in the spring, I want to have pretty much everything at least reasonably tuned in Sim, because there's only so much we can do because the tuning doesn't really transfer. But yeah, but that MVP should have everything done. Essentially, all we should have to do is tune it, which again, thankfully is a lot more reasonable this year, because all of the all the ROS problems that come up have been debugged in like the 8 months of last year's development, so it should be pretty straightforward. Though with that being said, robot localization is still randomly not giving us an ODOM topic, and I don't know why. So can't eliminate all of it, but most of it. All right, any more for software? Joe?
I don't know if this is quite software, but the camera that you guys have, you said this is a stereo camera?
It is, yeah.
So it outputs 2 images, or 1 image and 1 depth map?
So the nice thing about the OAK-D is that it has a ridiculous amount of customization. It has an onboard compute on it. We're not using it for much. It's the exact same one as the RealSense, actually. So you can, in the node, configure whether you want left, right, RGB, or what I'm currently using is the stereo. It automatically does the stereo disparity to depth image. And so you can act like it's essentially like a structured light or something, and not stereo at all. But yeah, if we wanted to do something with stereo, we could. It's just a configuration option.
It already gives you an image that at this pixel it's this.
Exactly, yeah. Thankfully it does that for us. Yeah, they have some sort of inference, because it's all for like, you can upload a model to it and it runs it. They have a model already to do that inference of stereo image to depth, essentially just preloaded. And so you can interface with that in the API instead of doing that all manually.
Okay. And then if you have multiple cones, does that mess up the depth image? I don't know exactly how stereo imaging works, but I know they have to map features in the 2 images, and there's multiple cones in the image. I assume that increases the error.
Not in our testing. For once I can say in testing this hasn't been an issue.
So you tested it with lots of cones?
Yeah, it's not hard to find cones. I was just messing with the depth a lot the other day. Really the biggest issue at depth, again, I'm not sure the exact algorithm that they use for it, is less that, but more if there's not enough features. So like a flat wall especially, it just gets nothing. For some reason the ground it does, which is useful. I don't know why it gets it off the ground. Maybe it just bumps and whatnot. But for the cones, yeah, it has no issue. It does as well, just more context. It has a max range on the spec sheet of 10 meters with like 20% error, which is pretty bad. So probably like 8 meters or so will be our like max range. Because outside of that, the issues you mentioned do start to pop up a lot more. But within the spec, hasn't been an issue.
Okay. So the cones are closest, which are the most important for taking the wave.
Yeah, of course. Yeah, I mean, 8 meters, it would be nice to go further, but realistically some cones are obscured at that range anyways. Because, if we're moving at 11 meters per second and 8 meters, you can do the math pretty easily. That's not a lot of time for us to do all of our stack. I mean, granted, a couple hundred milliseconds is still quite a bit, but, it's, if we could see further, it would be nice, basically.
I think I looked at the camera and it was like a rolling shutter at 60 FPS, so like at that speed, the close cones are gonna be like, just so you know. And then also,
Okay.
if you're doing object tracking and you run into a corner and you're doing IDs, you're gonna want to watch out for crossovers.
Yeah, that makes sense.
If you drop the wrong one, you're going.
Right. Yeah. I'm trying to think, because that would be. So we are including depth in that tracking, which is nice. Because there's depth. I'm trying to think, because we can think of this on like a 2D plane because you can just transform it. I'm trying to think. So it would be, you have the inner edge, you lose the tracks in all the inner edge, and then you don't want to jump to the outer edge that is still seen. Is that the problem?
I guess so. I don't know. I was thinking just for the color object tracking, if you have 2 cones, I don't know. The close and the far, I think you're
can drop.
Oh, like the blobs. I see what you're saying. Yeah. So that is something that actually we're gonna have to do more testing in. The way we'll have to test that, but I think the way we're doing the object like rejection for things that aren't cones but are orange, we'll have to see. That may reject those just because a lot of it's with the aspect ratio, and cones are of course rather vertical. So if you have like a really wide cone, I think it would just reject it preferably, and then we just do it fast enough that by the time they are separated, we capture it. But yeah, stuff like that is definitely going to be a matter of, test it and see benefit of. Again, I'm trying to get that earlier in the year and see if we have to make it a little more advanced than what we're doing. Very short tangent. One of the other teams from KSU, I believe, I think it was Georgia Tech, made a model to detect the cones, and they just have it on open source. So if we want, we can just kind of cheat and just skip this entire thing and just throw the neural network on it. I think that's a lot less interesting, but that is an option if we find out, like especially in March, that like, oh, this object detection just fundamentally doesn't work. We have that bailout option. But again, especially since it's the other team, there's some pride here. We want to do it correctly, do it ourselves if we can. Yeah, any more software? More software.
More thing. For your ECUs, I know you mentioned that you have data log of CAN. Do you have any debugging messages set up? How do you plan on debugging your code on the ECUs, I guess?
That also kind of remains to be seen, to be honest. Okay, I'll be honest. The ECUs are very simple. They're essentially, that's one of the main reasons I wanted to get planning off of them, was because in that case, they're essentially all just, we can't connect my Dell PC to 5 volts, Well, I mean, you can, it's USB, but you know what I mean? Like, there's no DAC on it that I can use. So they're all essentially, here's the command message, convert this to some analog signal or digital signal or whatever. So you can kind of debug them as units with like an oscilloscope or something even standalone, and then reasonably trust that they work on the bus. Since they're simple enough, we can kind of use that heuristic. But yeah, if we made it bigger, we'd definitely have to think a lot more of how we would go about debugging that. Cool. If we're done with software, I do want to give Jaden a chance to get some mechanical advice here. We're good. I think we're good. All right. Let's be relatively quick.
Shoot.
We have 20 minutes to do it.
Yeah. That's
Go.
cool.
The E-stop powers off the drive system and then half of the 24 volt system?
So it powers off the LiDAR and it powers off the
magnet.
Yeah, well, the magnet, but then also the steering motor, because it'd be really weird if it was like something's wrong and the steering motor starting to go fly back and forth, and then the LiDAR, we just want to.
But you want to keep the brake actuator running.
Yes, because we have. I mean, I don't care if we need to brake and it keeps braking.
Yeah,
oh
what
no.
I'm saying, what if the brake actuator is shorting out and crushing the
That's a good point.
the reservoir? Because the brake actuator with the current design can extend to I mean,
Which
you
I
were
yeah I
the
put
one
it
that
yeah.
accidentally crushed the first one.
Which, that's another issue, but yeah.
Yeah, so I.
That is something we would want to e-stop. I hear you.
Yeah, I also don't really see a reason to not to leave it running.
The one thing is like, is it funky? Like if it lost power, would it know where it is when you power back up?
Yeah.
Okay.
Oh, well, it doesn't. Remember, we have no global map. It's just all local, so it doesn't.
No. I mean like,
You have
the actuator arm itself. Like if you killed it fully extended, would it be able to rehome itself?
And even if it like for whatever reason doesn't, when you reset the
Just
brake
set
chip,
it to an initial point.
Yeah, when you unplug the the ceiling's leaking. When you unplug the the brake ECU and plug it back in, the first thing it does is set the actuator back.
Okay, so in that case we can throw it behind it.
I would just
That makes. I hear you.
I would delete it.
Yeah.
Dead. Except for the computer, that would be bad.
Yeah.
You go.
Do you want to pull up the electrical schematic?
Let's.
Though I don't. I changed it to a less grainy one, but it must have been in the not copy.
So, yeah, I think you only changed it in the copy sent to the alumni. Sorry about that.
Oh, I didn't know there was a difference.
In the one we sent out, this image is a lot better.
Can I just open it?
The next few slides, but sorry about that.
See, low voltage disconnect. I guess we'll start with.
Here, Ellie.
How does the e-stop work? Because you have a relay that's going into a double coil that's going into the positive of a magnet, which is going to the positive of a 12-watt node.
Yeah. So.
No ground.
Wait, what? Where are you looking? Sorry.
You got a relay.
Yeah.
Which is going into a fuse of a magnet into a 12-watt node.
This is
disappears
the ground
into.
bus.
Is this orange line
This,
going to the ground
well,
bus?
I had these
or
black.
to-
Yeah. These were originally black, but the idea is it's going straight into the ground. It's taking power
Okay,
from
then
here
what
and then
is-
ground here. This
oh,
is just.
you use the same color for labels as you did for your wires.
This was supposed to be black, yeah, but
Okay.
yeah.
Okay.
So
I
the
was very
idea is,
confused
sorry
with
about that.
that.
Yeah.
I was watching the magnet going into a 12
into nothing.
volt.
Yeah,
I
no,
was like-
sorry.
I was like, what?
Yeah.
is happening?
No, so this is just a label just to show. Oh, he's taking 12 watts of power total, just so I could easily add all the units together.
Yeah. I would recommend changing your colors so your positive is red, your negative
If it's black. Mhm.
and then your labels are not red or
Some
white.
other color. Yes, understandable.
Because it is kind of trippy reading this.
Mhm.
Because as of right now, nothing's grounded.
Yeah,
your LiDAR is floating,
I get
your
it.
brake is floating,
Yeah.
which is kind of weird.
The idea prior was to make all these lines black, and then it will be just connecting to ground just as a symbolism. But I 100% hear you. Red and then black and then different color.
Is interesting. And then how does the e-stop work? Because I'm seeing your relay outputs to a coil, to a second coil, to another
So-
relay, which goes to a solenoid.
This doesn't really depict it the best way, but the idea was we had a hard time coming up with a way for us to stop two different voltage sources at the same time using the same wireless e-stop that we have. So the idea was to use two different relays so that we have the coils connected to the e-stop. The e-stop powers down the coils, and so everything after the relay is going to lose power until the coils re-energize, which is when we lift the e-stop. And then these coils are both going to the same e-stop, and then we press the button, it's okay.
I'm sorry, I do not understand which way power is flowing in your circuit.
Boom, and then the coil is going to control everything after it. And the same thing for here. So he's the coil, and he's going to control everything after. Oh, what?
What voltage is the magnet being run at? Because I think I saw earlier in the slideshow.
It's
that
24 or 12. We can step it down to 12.
It has to go down to 12.
Hey, understandable.
Right?
Yeah.
Turn it to slide.
No. Yes.
We could get a 24 volt battery.
Yeah, this
okay.
we we were in the talks of getting a different one. It's different. We have both on there.
24, but we're not cooking the magnet.
Yeah, I was gonna
Yeah, no, we're not.
That thing will turn into
Yeah,
slag.
100%. We were talking about
Okay.
replacing. That's why it's different.
Cool.
But once we're on the same page, we're going to either step it down or get the other one.
Um,
Have you had to isolate the camera in the past?
We don't know. No, we haven't used this camera before. We had cameras last year. We never got to the point where we could use them. So that's what the testing this weekend is going to tell us.
Have you considered how you're going to dampen it? And all that? That wire.
That essentially, and then just like rubber padding. Will it be enough? We don't know, but we're gonna have to test. Yeah, it's not hard to test either. So you build something, it takes a day. You throw it on there and see if it works. What's up? Are you done? Sorry.
And then have you considered the grade of aluminum you're using if you're switching from steel for your base plate?
No, that's our measles staff is probably still 100. That's something I'd consult our measles staff for. So for machining and stuff like that.
now, why are you moving to aluminum from steel?
It's lighter. I could probably get away with.
Is weight a concern? Given 2 slides before that, you said weight's not a concern, so you can do lead acid batteries. You gain significantly more weight from going from lithium to lead than you do from going steel to aluminum.
I just want to get aluminum plate for the brake actuator because am getting really sick of lifting that entire thing up, to be honest. Like, literally, we have the money. We can get an aluminum plate. It just makes my life easier at the end of the day.
Just be careful with your thicknesses and your grade.
Yep.
You are playing with enough force to where it can start to
Bend,
I'm
yeah.
pretty sure, didn't we bend the test plate last year with the actuator?
Yes.
It will bend it. And didn't we bend, was that a steel plate?
It was a thinner steel plate.
It'll bend the steel plate. So I would
So I do
definitely
a
be careful,
it-
given we bent a steel plate, I'd be very careful with an aluminum plate.
Yep.
definitely make aluminum work. Just consider your forces and
I hear you guys. Yeah. What's up?
For the e-stop, have you considered using a bike brake that's just cable pulled? So that way you don't have to worry about any kind of like building any kind of hydraulic pressure in a system. Just like a basically like strap a bike rotor and a bike caliper to it, and then literally just have the spring and lever rip on a cable.
Yeah.
That
I
way-
don't know if you ever looked at it, but it's kind of what they did on the power cart like a decade.
Yeah, I don't know.
I think they still have those.
I don't know if it would actually lock the wheels, but I think you would get enough stopping power out of it to stop within 10 meters is a lot of distance.
Which
I
is
think you'd get enough stopping
which
power.
is kind of where we're at right now. The one thing I liked about just duplicating the rotor is it is simpler to design and to just manufacture. You just throw another one on there. Also, like I know like we're able to test it now with the brake that's currently on the cart versus what you're saying. There's a lot more unknowns, and for me, I have a lot of mechanical design to get done, which means on the current design, I can keep a lot of the stuff the same from last year, and kind of play with that 10 meter instead of locking the rear axle, which hopefully will give me enough play to be able to successfully create a finished product, and then maybe improve on that for next year. What's up?
Because I know that, like, I just don't want to worry about you guys, like, gaining air bubbles in your e-stop braking system and not knowing about it.
Yeah.
And all of a sudden, you don't build hydraulic pressure in your e-stop.
The other thing is
that is why the brakes don't work.
Yeah. The other thing is like, I feel like scope creep is making a reappearance again. You mentioned that you had concerns over 14-mile-per-hour cap. Given the fact that the fastest vehicle ISC's ever released was 4.4 physical cap while teleop, and I'm pretty sure none of our autonomous systems have exceeded half meter per second. I feel 14 mile per hour would be a phenomenal feat for this program, especially in this given time.
So you're saying like
I'm saying given your
keep
manpower,
the design as it was last year?
Yeah, I'm saying given the manpower, you might want to consider not completely redesigning the e-step system and focus on like integrating steering and stuff.
I hear you.
Because again, like 14 miles per hour, that would be genuinely a feat for this program. Like it would be probably 20 times plus faster than anything this program's made before for the 25-ish years we've been around.
Which is true. I mean, I guess I hear you there. I mean,
You're a spec. And software can kind of do whatever. It just makes it easier on our end if it's slower.
Because like realistically, like we are making a huge jump in quality of system and speed. Like getting to even Auton at 5 miles per hour would be a genuine like accomplishment for this program.
I hear you. Yeah.
And I worry about like a hydraulic. I feel like a hydraulic e-brake.
Hydraulic's gonna hit you. The other thing is, I don't know if you look.
Room for failure.
Have you calculated your range of motion needed for your lever system?
No,
I do
it's.
see Bam's question. Yeah. Bam, your question will follow once I'm done with this little thing.
Can we?
Only because how far of an actuation do you need on your reservoir in order to get full brake pressure? It's probably what, 2-inch movement.
Probably.
2-inch movement. You're at a 9-to-1 lever ratio with an 18-inch swing arm.
There isn't much travel.
Yeah, to get that 2-inch movement, your arm's gonna be swinging what, 18 inches in order to get that total travel.
Yeah.
I'd be interested to see where you find 18 inches of space to swing.
Facts. Yeah, I hear you. I mean, I'm not complaining about keeping the design we did from last year.
Yeah.
I guess for me, like at this beginning of the year, I'm like, right now is the time that we have to try to come up with a new e-stop solution, bring it to PDR, see. But I mean, hey, no complaints about keeping it the same. I wouldn't like to be the limiting factor in terms of how fast we can go, but I think I agree with you in terms of 15 miles an hour. I think if we can have something going autonomously at 15 miles an hour, I think that'd be really impressive.
No
So.
offense to Andy, but I don't think you're gonna reach that speed this year. Like, I don't know, just based on how hard autonomy is.
Depends on tuning.
Yeah. And then, Bam, your question really quick. So right now, we're gonna have to step it down to 3.3 volts. That's an issue we knew we had, and that's kind of why we wanted to kind of switch it around to whatever power circuit. Bam asked. He said some TNCs can be damaged if they get more than 3.3 volts at any pin. We're also gonna have to do some different controls in terms of powering the steering motor. The steering motor needs 5 volts. The TNC only has 3.3, so we're gonna have to step that up as well. But that's stuff we've considered. We just haven't designed those circuits yet. What's up?
Sorry, Les. I thought that we
Sorta.
I thought it was on a bracket that was like drilled into the plastic though. Like
That part was, but the thing inside was just like screwed into whatever was in that motor.
Yeah.
So if it goes either direction, it could start pulling itself out. Also, like, was it really mounted securely? It was mounted with a piece of tube that was stuck onto a piece of metal that was.
Hey, that is the piece of tube we've used for 15 years.
That is true.
True.
That is a giant tube.
As all of the alumni will agree with.
I don't know if it's.
But we're also gonna be going faster than we've been going in the past. That thing's gonna be whipping around, and I just don't know if I trust that tube. I just don't know.
I also because I know that you guys mentioned the like the traditional like automotive wheel speed sensor.
Yeah.
Lord have mercy. Is there any thought about mounting for that? Or?
So essentially, it's just this little pill. So essentially, I mean, wherever we have that mounting bracket that we're gonna have to remake. Whether or not we remake it with a second caliper or not, we're gonna have to be modifying that guy. So you just modify that with a little arm that points to the brake rotor. Very much simpler than that encoder. Also, like, I just get so scared of that little encoder. We'd have to mount it a lot stronger than the way it was before. There's not a ton of real estate around the motor as it is now, so it was just good. It would be a lot easier to mount it off the brake. So, but the one question is, like, combustion uses that, and they just throw it into their ECU, and it handles kind of the output for that. We don't really have one that's just like a digital in-out 1-0 type thing. We're having trouble finding one that works. We're kind of nervous about interfacing with it all because it's just like an unknown variable.
There's also no documents for any of them, and it's terrible.
I mean, it's a.
Sup, Joe?
The encoder or the wheel speed sensor?
That little magnetic pill wheel speed sensor.
I mean, I know that the combustion car uses like real like axles that have actual.
Well, they essentially do the rotor thing where they have the Spencer and they have like those little slotted rotors. But the problem is they just throw it into, I forget the name of their ECU is, the Motec does that all for them. Joe, what's up?
So your implementation question is like how to get the data from the sensor?
How to interface with it, because a lot of the ones are like we can get it to you from China in 2 months. Like there's not a ton of documentation about it, and
So is it just a sensor that's 1 if it detects the magnet and 0 if there's not?
I'd love if that was the case. We don't know.
There's literally no documentation on it. It's really annoying. It's like, I feel like it's one of those things where I think it's like, oh, it's so simple. Let us know. They're automotive engineers. Then we have no reference. So I haven't been able to find anything.
Have you had a chance to measure the output?
Oh,
We don't have one. The thing is, this is where like we aren't sure if that's the direction we want to go. I'd love for us to go that direction. It's just like we ask Combustion, they're like, oh yeah, we just throw it into Motec, and Motec does it. So I mean, if anyone like has a free couple minutes and they want to go find one and
I have one.
that you know how to interface with,
No, I just have one. It was for the fit.
literally give it to us. Oh wait, I have to hear about that later. But
requiring ABS is a skill issue. So
oh my god. Wait, but did it work? Did you actually run at Lemons? Did it go well?
Brand new.
Did you run at Lemons though?
No, not this year. I figured
I would have heard about it if you ran. Sorry, we're getting on a tangent. Can we use it and see it and try to play with
I
it?
don't have it, but yeah, I could get it.
Okay, yeah, because we just need something we need to try to play with. We didn't want to order something in 2 months. Perfect. That would solve a lot of work because we could totally use it. We just were like the software guy. We were just nervous because we didn't know how to interface with it, and we didn't want to go down that road when we have an actual encoder that we could. If we really wanted to. Sorry.
Like again, it's
I didn't mean to.
my boys at Rock Auto will sell you as many of these as you want.
Well, also, if I ordered it, there was one you can order it for 1,000. You could get only 1,000 off of DigiKey. Only 1,000 of the little sensor.
No. We can mass produce. I'll show you.
No, literally. Well, yeah, there you go. So that was that. Other hardware questions.
Yeah. Question.
2 minutes, go.
You mentioned for your main fuse that it's fused at normally you fuse at 300. You're fusing at 315 to quote be safe. How is increasing the current safe? Given the fact if the system's rated at 300, you've now increased the amount of amp that can go through it. Typically, if you want to be safe, you fuse low, so it kills more.
Maybe 15 was a little too much.
Well, I meant, what is the goal with increasing the amount of amps that go through your system? If it's rated for 300, why are you fusing
the 300 value when the motor starts up? How much
It's the max. So it's going to start at 300 and then it's going to go lower as you run
You
it.
don't want it to trip right when it's drawing the
You don't want it to trip out. It's like because 300 we went. I fused based off the max.
Yeah, I was confused by your terminology of saying to be safe.
Sorry, yeah.
I was like, typically you want your fuse to blow and then you go, oh, my bad, overcurrent.
Exactly.
If you mean just having tolerance, so is this not the provided drive system that Top Cart spec'd a fuse for?
From what I tried to look on the top car on the specific motor, I couldn't find a specific number for the fuse. All I found was that it was 300 amps or something like that, and so I just went to 215.
Because unless you guys are redoing,
It does say 300.
300 amps,
Yep.
yeah. So
yeah. So I would, given that this is the power circuit provided by a international go-kart supplier, I would just leave their spec alone.
okay,
That was
so
part of our mindset
Which is what
last
we've
year.
been
100%. We can keep
Yeah.
to 300.
Yeah.
It's
I
not a
just
deal.
wouldn't want to
Go with too much, yeah, 100%. Mhm.
More hardware.
I guess maybe one thing.
I would say there's a 250 amp
to
fuse
look
right here.
into.
Yeah, I was gonna say, isn't it?
Oh,
Sorry.
yeah.
It says it in there. Sorry, go for
Yeah,
it.
the fusing.
Yep.
Maybe look into fuses that are slower glow ones as well.
Mhm.
Like get the speed of them for dealing with the inrush thing.
Yeah, I think there should be a beefy one that I'm. There's one
We're-
already on.
Hey, perfect.
The answer is we're not changing the stock circuit.
Yeah.
That 48 volt circuit, we're not changing with those
Yeah.
batteries. Is
Yeah.
the short answer. to
I
that.
think there's already a slow blow automotive fuse built into the system from Top Cart.
Yeah, I have faith in that fuse. We're not. Yeah, go for it.
Oh no, I just because you said you weren't changing it, but there's a 350 amp fuse. Is that?
It's just prior to
Oh,
the
that's
actual.
right. Oh, okay. I
I guess
9 p.m.
I'm gonna say if there's any other questions, shout them out now before we get kicked out by the guy who walked down the hall. We'll see, but we're
Pretty
invisible.
soon.
If we just stand very still, we won't.
If we turn off the lights, maybe we'll see.
So there's 4 batteries here, and then there's isolated batteries for each of the microcontrollers.
So each of the microcontrollers has like little, like tiny little, like.
The lipo, like
The small
Right.
AA battery
Why not
things.
just use converters and
And step it down.
Issues we had in the past was like voltage jump from. Something we like to do is just like isolate all of our circuits. It makes it easier to troubleshoot. Also,
that's the
just like.
transients you were telling me about.
Yeah. So that happened in the past. It killed one of our lidars a couple of years ago. We're terrified of it. We keep them separate. Is it the most efficient way? Can we change it later? Sure. We're gonna keep them separate for now.
The mindset last year too was, again, this is an entire circuit system provided by the cart provider. My mindset was I want to leave it
Don't touch
alone.
it.
Yeah,
Keep
because it
something
works.
that works. Yeah.
Yeah.
Okay.
Thanks, Bam. By the way, Bam's dropping off.
Oh.
Thank you for showing off. Thanks for the
I mean,
advice.
appreciate the advice.
So thank you, Brandon. I don't know if he's leaving. He said great job.
Yeah, we need to
9
have a
p.m.
chat monitor now.
Yeah. Any other quick questions? Cool. Appreciate it, guys. Thanks for taking up your Friday night to come give us advice.